Okay, so the purpose of this section is pretty straightforward, so I won't need to say too much. Really, what this section is going to be about is we're going to develop rules that are going to allow us to take the derivatives of trig functions, like sine, cos, and tan, for example. Okay, and before we get underway, I want to remind you of a few things about sine and cosine. In particular, I want to remind you of a few identities. So the first one is that if you have sine squared of any value plus cos squared of that same value, it's always equal to 1, no matter what the value of x is. Okay, that's the first identity I want to remind you of. And the second and third one, there's one for each sine and cosine. It tells you how you can expand expressions like the following: cos of 2x or sine of 2x. So there's one identity for sine and there's one for cosine. So for sine, this is equal to 2 times sine of x times cosine of x. And for cos of x, or pardon me, for cos of 2x, it turns out to be equal to cosine squared of x minus sine squared of x. Really, you might ask what the payoff is here. Because the right-hand side of this equation, for example, looks a little bit more intimidating than this side, maybe. There's only one trig function over here, but here there's cosine and there's sine, and they're both squared. But the payoff is that you actually cut the argument in half, and the argument being the thing you're plugging into the function. So if whatever your angle is here, you're only going to have half as much here and here. So you're basically getting rid of that 2, which depending on the situation that you're in, this 2 might be a problem for you, maybe making things difficult. So you could be going in either direction, but these are referred to as the double angle identities. And actually, let's write that down now. So these are called double angle identities. So they're called double angle identities because if you're plugging 2x into sine, you're really plugging double whatever x is into sine. So if you think of x as the angle, in this case, you can see where the name double angle identities came from. The first one, sine squared plus cos squared is always equal to 1. That actually comes from the Pythagorean theorem. So this is actually referred to as the Pythagorean identity. And there's one other one I'm going to remind you of, and it goes like this. If you have the sum, it's really a more generalized version of this second equation that I've written here with sine of 2x is equal to 2 sine x times cos of x. It's a more generalized version of that rule. If you have two values, x and y, and you add them together and plug the sum into the sine function, you can actually write this in terms of sine and cosine of just x and y, and if you put them together properly. So here's how you do it. You can write this as sine of x times cosine of y plus cosine of x times sine of y. And what this one is called, this actually has a name as well. This is called the angle addition formula for sine. I'm just going to write angle addition formula. There's one for cosine as well, but we're not going to need it here. But you can look it up. There is one for cosine as well, and I recommend that you look it up. But we won't need it, so I won't remind you of it just now. And we're actually also going to need two other things, and this should be new to you. The next thing I write down will be new. So these are reminders, but what we write down afterwards is going to actually be a new principle. But these are referred to as limit identities, and here they are. There's two limits, and these are actually quite technical to actually evaluate from scratch. So what I'm going to do is I'm just going to give you the values, and we're going to take these as axioms, which really just means we're going to take them as fundamental truths or starting points. We're not going to look too deeply at why they're true, but we are going to look at how to use them. So the first one is as follows. If I look at the fraction of sine of theta over theta, and I ask the question, well, what happens to this fraction as theta gets really, really small? Well, it turns out that this fraction actually approaches 1. So for values of theta that get very, very small, sine of theta and theta become indistinguishable. That's another way to phrase it. So that's the first one. And the next one is the limit as theta goes to 0 of cosine of theta minus 1 all over theta. So what happens to this fraction as theta gets very, very small? And it turns out that this fraction approaches 0. So again, I'm not going to prove these to you at this moment, but I will ask you to just take them as fundamental truths. So we're going to focus on the application of these identities. And the first application is going to be that we're going to get a derivative formula for sine of x. Because right now we don't have one, right? We can handle powers, we can handle exponential functions as long as they're the natural exponential function. And what else can we handle? We can handle radical functions like square roots, cube roots. We can handle products and fractions, no problem. But there's still lots of functions we don't have rules yet for to take their derivatives, and sine of x at this stage is one of them. But we're about to take care of that right now. So as you can see, for example, let f of x be sine of x, and we're going to compute its derivative. So we're going to compute f prime of x, and we'll just work it out using the definition, because what else could we do right now? If you don't have a rule for a function, you have no choice but to use the definition of the derivative if you want to take its derivative. So that's what we're going to do. So we're going to have to go the limit as h goes to 0 of f of x plus h minus f of x all divided by h. Okay, so that's the limit definition of the derivative. And then the very next step is pretty much always going to be just replace the function f with what it actually does, which is if you plug in a number to the function f, it returns the sine of that value. So let's apply that here. So this is really the limit as h goes to 0 of sine of x plus h minus sine of x all over h. All right, so that's the first step. Now, you always want to ask yourself before you start a limit, what happens if you plug in the value, right? And if you do plug in the value h equals 0, you're going to get sine of x plus 0 minus sine of x on the numerator. So you'll have sine of x minus sine of x, which is 0 on the numerator, right? And if you plug in h equals 0 to the denominator, well, you're going to get 0 on the denominator as well. So this really is a 0 over 0 type at this stage, which, remember, that tells you absolutely nothing. It doesn't tell you what the limit is. It doesn't tell you whether the limit exists or not. It just tells you that it's way too early to plug the value in, right? Or I shouldn't say way too early. It could be just a couple steps too early, or it could be one step, or it could be many steps too early. But in any event, we're not ready to plug in the value h equals 0 just yet. We need to do some work. But what can we do? And this sine of x plus h, if you remember one of the identities that we looked at, or the angle addition formula up here, you can see that we have a rule that tells us what to do if we plug a sum of two values into the sine function. So this is a great time to use that rule, where instead of y, we have an h. That's okay. So what are we going to get? We'll have, well, everything else will stay the same. Limit as h goes to 0. So we'll have sine of x cos of h plus cos of x sine of h. Right, that's what I would get if I carefully apply this rule to expand the sine of x plus h. So this is a case where it's really this x plus h makes things difficult. It makes it hard for us to do anything. So this formula gave us a way to expand it and write sine of x plus h in terms of a whole bunch of sines and coses, but each of those sines and coses only had either x's or h's plugged in, not x plus h anywhere. So that's the payoff there. And of course we still have I don't mean to keep sliding this around so much, we still have this minus sine to worry about. So let's subtract that out afterwards. So minus sine of x, and then the whole thing is going to be divided by h. Okay, so all we changed was we expanded the sine of x plus h. Okay, what's going to happen next? Well, we're actually going to split this fraction up a little bit because it's a bit too much all in one fraction to see what's happening. So what we're going to do is we're going to write this as the limit as h goes to 0. So I'm going to split this up into two fractions that are added together. The first one is going to be cos of x sine of h all over h. And really what I've done, this cos of x sine of h, that's just the middle term here, right? So we've got the first term and the third term left. We're going to put those in the second fraction. So this is going to be added to the following fraction. Sine of x cos of h minus sine of x. And that's all going to be over h. Right? And you can, if you were to add these fractions together, you can double check that you really are going to get the fraction in the previous step. We're just decomposing this into the sum of two fractions. And the reason that that's useful will become clear in a couple of steps. But for now, I want to separate or decouple, in a sense, or a factor would be a better word, except it's already a single term. But write these as a product of two factors, one of which has all the h material in it, and one of which has all the x material in it. I'll show you what I mean by that. So really, there's this cos of x that is completely independent of h, right? Multiplied by sine of h over h. So let's separate those. Really just going to write it slightly differently. So writing it as cosine of x multiplied by the fraction sine of h divided by h. Right, and if I were to multiply the cosine x onto the fraction, I would certainly get exactly what I have up here. So I haven't changed anything. And then here, we actually, the numerator, both of the terms in the numerator, they both have a common factor of sine of x. So I'm going to factor out sine of x from the numerator, but also pull it right out of the fraction. So what I'm going to get here is sine of x times cosine of h minus 1 all over h. Right, and that is what we get if we do this. You notice that's what I mean by each of these terms. I'm just writing it as a product of all of the x material. So the part of this expression that's independent of h multiplied by the other part of it, which is independent of x. Same with over here. This fraction here was equal to this expression sine of x, which is independent of h, multiplied by this fraction here, which is completely independent of x. But actually, now you might ask the question, well, why is this good? This almost looks like I'm making things worse, maybe, right? But it actually doesn't. And the reason I split it up like this is so that we could take advantage of these identities now. Because remember, if you take the limit as theta goes to 0 of sine of theta over theta, you get 1. Well, what about sine of h over h? Well, as long as h is the thing going to 0, the same rule applies. Right? It makes no difference what you call the variable. Right? So this fraction here is approaching 1 as h approaches 0. And this fraction in here, we can apply the other limit identity. Limit as theta goes to 0 of cos theta minus 1 over theta, well, that actually gives you 0 based on this identity. So again, down here we have the only difference is the variable h. But still, h is exactly the variable that's going to 0. So it doesn't matter what you call the variable. This is approaching 0. So you have a limit of a big expression here. This fraction is going to 1. Cosine of x, well, it's not constant because x is a variable, right? But as far as this limit is concerned, it is a constant because x is completely independent of h. So you can treat this like a constant. So you have a constant times something that's approaching 1. This whole term is just going to approach cosine of x. And this term, for the same reason, you can treat sine of x as a constant because x is completely independent of h. And as far as this limit is concerned, h is the only variable. So you have this term is sine of x times a factor that's approaching 0. So this whole second term is really just going to disappear. And really what you're going to be left with, finally, is cosine of x. Okay, so that, well, hey, and that was the derivative of f of x. That means the derivative of sine of x is cosine of x, right? And that's actually pretty neat. You might expect a really, really weird answer that would be difficult to wrap your head around, but actually, it turns out that the answer, the derivative of sine of x, is wrapped up really nicely in another sinusoidal function, namely cosine of x. So let's summarize. So therefore, if I write this in operator notation, I can say the derivative with respect to x of sine of x is equal to cosine of x. And actually, in a similar manner, you can follow this approach almost exactly, and you can show that the derivative of cosine of x can be similarly obtained. And I'm not going to work through that one in detail. I'll leave that to you to check as an exercise, but I'll give you the rule here while we're at it. So let's start the sentence over. So therefore, the derivative with respect to x of sine of x is given by cosine of x. That's the part we just proved. And in a similar fashion, we can say that the derivative with respect to x of cosine of x, and well, if you had to make a guess, you might guess that it's sine of x, right? Since the derivative of sine of x gave us cosine of x, you might think that, well, maybe when you take the derivative of cosine of x, you get sine of x. And if you made that guess, you're almost right. You just have to change the sign. So you actually get negative sine of x. Okay, so those are your two rules that will now allow you to calculate the derivative of sine of x and cosine of x. So if you have a weird function that you can handle except for just a pesky appearance of sine or cosine, you now are equipped to handle that function. And by handle it, I mean take its derivative. So let's look at a couple of examples in the next clip.